All right. Hi, everyone. Thanks for joining us this afternoon for this afternoon's Wheatland seminar. My name is Tony Guay. I'm a remote sensing specialist with the Wheatland Geospatial Lab here in the School of Forestry Resources. And just by way of introduction, we're very pleased to have Dr. Cassidy Rankine with us this afternoon. Cassidy is a remote sensing specialist and commercial application specialist with 10 years experience in academic and commercial R&D in the use of remote sensing technologies. He is a naturalist and tech enthusiast with expertise in the utilization of emerging remote sensing technologies and AI leveraged spatial analytics for natural resource management, sustainable development, and risk mitigation. Cassidy has a background in biological and environmental sciences and has 10 years of experience developing high-tech solutions for monitoring land, vegetation, and water dynamics for both research and commercial applications. He holds a PhD in Earth and Atmospheric Sciences from the University of Alberta, where he worked to develop an international network of Earth observation satellite validation sites for modeling forest ecosystem productivity time series in response to anthropogenic global change forces. So with that, I'll just mention, please, if you have questions, either hold them to the end of Cassidy's presentation or go ahead and submit those questions in the chat panel, and we'll respond to those at the end of the talk. With that, I'll just turn it over to Cassidy.
Great. Thanks, Tony. Thanks for the intro. It almost sounds like I wrote it. So thanks for having me on this Wheatland seminar series. I've watched a few of the previous ones, and you've got a pretty impressive lineup in your history, especially with the focus on forestry. So it's a pleasure to be here. And I'm coming to you today from Alberta, Canada. And hopefully this talk will be a much sought after distraction from the craziness of the politics going on right now. However this election turns out, we just want the Americans to know us Canadians will be here for you. Physically, we can't really move the country. We'll be here. And that's all I can say on that. So today we're going to talk about what we've built at HRIS Systems, which is a company I'll talk a little bit more about, of which I've been a part of the team for 2 years. And today we're going to look at high resolution forest inventory and some of the work we've done around wildfire damage analysis in British Columbia, Canada. And as Tony mentioned, I have my PhD in remote sensing, and I came from an applied Earth observation systems laboratory here in Edmonton, Alberta, at the University of Alberta, where we focused a lot on looking at the accuracy and calibrating Earth observation satellites. So I have a long history of going to remote locations and forests all over the world, setting up instrumentation and calibration validation equipment for things like carbon balance, net primary productivity and gross primary productivity, looking at phenology and looking at the changes in forests on the scale of seconds to decades. And so a lot of that experience I've brought to the table with the work we're doing in forest inventory at HRIS Systems with our high resolution inventory solution, and finding ways to use satellites to update inventories after disturbances, and wildfire being a major force of disturbance. That's an area of a lot of interest. So here's a quick overview of the talk today. And I'm probably slated for about 40 minutes of slides, and then we'll follow up with questions. So I'll discuss who we are at HRIS, which is what we call our high resolution inventory solution product. What we've developed for this wildfire mapping application, and hopefully what you could take away is, why we've developed this solution, and how this high resolution inventory has made it possible and perhaps has allowed us to do some more research oriented analytics that are otherwise not possible without the type of level of detail we're getting in the forest inventories we create. And then I'll demonstrate what we've built as an online tool for our HRIS inventory and update services. So the big overarching questions I hope that everyone can take away some answers to are, why do we want to measure fire severity or fire damage severity? Why we might want to predict that on a forest management area, and what is a high resolution forest inventory, and how can it benefit forest managers for disturbance mapping and updating inventories, and to anticipate risks from forest fires and other disturbances. So you'll hear me say HRIS a lot. That's HRIS, High Resolution Inventory Solutions. We've been building this product for probably 15 plus years of research involved in this forest inventory solution I'll talk a lot about today. And really the goal was to improve our understanding of what is on the land base from a forest management perspective. And once we created this higher resolution inventory solution, many different applications of that data began to emerge. And wildfire is just one of them, but I'll touch on a few others right here at the beginning of the talk. So we've got a small but powerful team at Tessera, and we've been remote for many years. One of the first to transition to a fully remote, cloud-based, cloud-first approach to software development and geospatial application development. It's a Canadian employee-owned company. Bruce MacArthur is the CEO who put the company together in the late 90s, and he himself comes from a forestry background. And he was managing forests in the BC interior and the BC coast in Canada, and realized that they were really limited in what was possible with existing inventory solutions. And he envisioned a future where computing power and remote sensing technologies would come together to create a new era, essentially, for reliable inventory, and no longer be stuck with the limitations of ground-based cruising efforts to get your inventory needs met. So we've got a team of software developers. A lot of them are, cloud software engineers, a bunch of GIS development experts, and a great team of forestry managers. I can't fail to mention Dr. Ian Moss, whose career of research in forest inventory solutions has taken us on the path of creating this very advanced and accurate inventory solution. So he's a key contributor to a lot of the research that goes behind what I'll talk about today. What sets us apart is species prediction as one piece of our inventory, is getting really accurate, high resolution species estimates, as well as site index metrics. So the productivity of each stand or microstand on the landscape. We generate stand and stock tables for every polygon, which is something that's a very complicated task that not many people are doing at the level of precision and accuracy that we're doing. And of course, an inventory, as soon as it's generated, depreciates. The forest is always changing, the landscape is always changing. So being able to update this inventory that someone has invested in on a regular basis, on an annual basis, let's say, is something we're heavily focused on. And that includes growth and yield, and being able to detect disturbances at multiple scales. Those of you who are familiar with LiDAR-based inventories will know the basics of how a very high resolution inventory might be generated. And so we follow an area-based method where we grid the landscape into 20 by 20 meter grid cells, but we also use computer vision to delineate the stands into uniform units called microstands. And we have a very dedicated and deliberate ground plot sampling regime to make sure we get representative sampling on the landscape of the species of interest and the different, sub biomes in the forestry domain. But it's essentially, ground plots that are correlated to very high density, high spec LiDAR collection, color infrared aerial imagery, and paired as well with satellite observations to create an upscaling of ground data to the landscape level. Canada has been promoting these enhanced forest inventories using LiDAR for many years. And there are some similarities with the leafy and the EFI inventory methods, but we go beyond what those offer because we're essentially starting from scratch and creating a very high level of detail that you can't get with classical inventory or enhanced LiDAR-based inventories. I'll be referring to our microstands throughout this talk. And there's a picture here of what they look like. Essentially, we're using computer vision to analyze some of the different raster derivatives from LiDAR point cloud density metrics, stand height metrics, as well as some color infrared indices that are indicative of species groupings to create these uniform and automated and scalable microstands. These are on average just under half a hectare in size. But they range anywhere from about 0.2 hectare to about 4 hectare, depending on the uniformity of the stand. So this is our base inventory unit that we're able to use for our analytics reasons and inventory reporting. Now, as I mentioned before, once we developed this microstand-based approach, we realized that there was many other applications out there besides just core inventory for forestry that this data is useful for. All types of different vegetation management. We're a strategic management and sustainable management first approach to inventory and forestry. And sustainable forestry is extremely challenging if you don't have the right intel on the landscape and the land base. And so, we incorporate very detailed maps for road planning, hydrology networks. We've used our inventory for things like habitat assessment, winter mule deer, overwinter range modeling and prediction is another application of interest that we've done with HRIS. And of course, what we're going to talk more about today is this fire hazard assessment and wildfire mapping. So looking at wildfire disturbances, we know that they can be very destructive events, and having a good quantifiable metric for how much of your inventory has been affected and to what degree your timber inventory has been affected is very valuable information that traditionally requires a lot of boots on the ground, as well as aerial missions, scouting and helicopters and Cessnas and drawing fire boundary maps, and some of that is beginning to get replaced by remote sensing methods. And we keep getting the question from clients that we work with on, can you help me with my fire management plan, and how can we use this inventory to predict where I should focus my efforts? I've got a huge land base and forest management area to manage, and I need to use my limited supplies more targeted. And so we've spent some time approaching this problem, and it's not a problem we anticipate that's going to be going away anytime soon. So just to take a step back, look at the big picture of things. So the Earth is a very unique planet in that the surface of the Earth is bathed in oxygen. We've got a very oxygen-rich atmosphere. And what that does is it promotes complex life as we know it. We've got all these higher level organisms that thrive on this oxygen. On the flip side of that, oxygen is highly combustive, highly reactive. And so the Earth's surface is always in this balance of slow combustion, which all life forms are doing. Every time you breathe in, you've got this very slow combustion reaction powering your body. That goes for all living things on the planet. But it doesn't take much to turn that into an extremely volatile exothermic reaction. A lightning strike will start a fire. And so fire on the surface of the earth is hand in hand with the biosphere. And it's surprising when you zoom out and you look at the earth at a distance. We've got this map here shows all reported fires from 1960 to 2000. This was a meta-analysis from 2000. And each one of these pixels is the proportion of the area burnt on an annual basis. And so you can see very quickly that basically anywhere that vegetation exists on the Earth's surface has some degree of fire present. And so we live on a fire planet. And though we don't live directly in the path of fire always, it's not something we can ignore. And it's becoming more and more of a problem for humans as we build and live closer and closer to that forest fire frontier. Zooming in a little bit, looking at North America, here's a map. That is the recorded forest fire perimeters accumulated from 1984 to 1999. The red is Canada, and the orange color there is the US reported forest fire boundary. So we could see it's very prevalent on the landscape. There is a research, there was a study done, published in 2015 that estimates that the fire season has lengthened by 25% on the Earth's vegetated surface since essentially 1980. And so we know we can expect forest fires to become an even more dangerous and very frequent problem to manage in the coming years, in the coming decades. Zooming in a little bit more, getting closer and closer to our study area that I'll be talking about the case study today. Here is some work done by Nicholas Koop's group about 10 years ago. This is a MODIS-derived fire presence map. So each one of those pixels is 1 square kilometer, and essentially just shows in a shorter time span. So the year 2000 to 2009, at least one fire was detected somewhere in that pixel over that period. So again, just to show fire is very prevalent on the landscape over even short time periods. A good proportion of the landscape does have some level of fire interaction on a regular basis. What does this have to do with forestry? Well, we all know very well that global tree cover loss is quite significant. This map here shows in green tree cover in North America, and the pink is the tree cover loss since the year 2001 as measured from Landsat. And you can get onto the globalforestwatch.org map yourself, take a look and explore these different layers. It also has layers for tree cover recovery and regrowth. But we can see there's a lot of forest area that's been lost just in the last 20 years. The chart on the lower left here is actually the proportion of tree cover loss from forestry activities in green and forest fire in red. And it's usually over half. Most years, more than 50% of the forest loss is due to fire activity. And you can see some swings and some ups and downs. This is the last 20 years. And yeah, it's a very notable trend that we've got a good proportion of tree cover loss due to fire. So this is a remote sensing group that I'm told I'm talking to, and I'm a remote sensing nut myself. So let's take a look at some satellite-based imagery of forest fires. Now this one, some of you may recognize, this is the Camp Fire in California, a very recent fire. It was absolutely devastating. But we're at a point now where the technology with the imaging sensors we have in orbit are able to capture a great level of detail on forest fires. And the magnitude of these fires really only comes into the full picture once you can see it from space. So just to get our mindset you know, in the frame of mind of what wildfires look like. There's a few shots I'll just scroll through here. This is in the boreal Russia, just looking at the burning front of the wildfire. Getting even closer, the awesome power of what a wildfire can do up close is just staggering. I did some research in Australian forests a number of years ago on carbon flux monitoring. And the foresters down there told me that when those eucalyptus fires break out in the eucalyptus forests, they are hard pressed to outrun them in their vehicles, in their trucks. These things can go up to 100 kilometers an hour as the gases of the vapors of the sap in the air of the forest literally explodes. So this is a pretty impressive feat of nature. As the fire dies down, we get all this smoldering. We get you know, ground fires that can burn for weeks on end. In some cases, months or years. Ground fires have been known to stick around. And then when the dust settles, you've got a landscape that is burnt to different degrees or different severities. Some forests are very fire tolerant and very fire resistant. If a fire comes through very quickly, you may just have a crown fire, and that may not do quite as much damage to the ecosystem, whereas slow moving, high temperature fires can come through and do quite a bit more damage. Even though they may not appear to be as severe of a fire, a slow moving fire can have longer lasting impacts on an ecosystem. So this is a key distinction. If there's anything you take away from the talk today, it's this, that fire intensity and fire severity are different things. Fire intensity is essentially how much heat is produced from a fire. It's a very instantaneous or short-term metric, but it's an absolute metric of the intensity of the fire itself. Fire severity is what we're going to be looking at today from a remote sensing perspective. And that's the impact of that fire on the ecosystem. So how did it affect the vegetation? How did it affect the soil? What kind of damage do we see to the leaf litter, to the seed banks? That is a much more difficult parameter to quantify and have an absolute metric for. And it's very dependent on the ecosystem and the vegetation type you're looking at. So I mentioned before there, a slow moving fire, a very low intensity fire can have much more severe complex effects on a forest ecosystem than a fast moving high intensity fire. So we're not going to be talking about the intensity, we're going to be talking about the severity of the impact. So there's not as much work as you might expect that's been done on tree mortality and impact of forest fires, because we have a loosely defined definition of how fire actually causes tree mortality. This is a figure from the U.S. Forest Service on actually trying to specify different mortality drivers of a forest fire. But essentially, foresters and forest managers want to know, what have I lost in terms of my tree stock and my timber stock? And is a tree that is burnt actually dead, or is it going to come back very quickly? And those are hard questions to answer, having a cursory look at an area that's been impacted by wildfire. So let's dig into some of the methodology that we used here to actually measure wildfire severity from space. And it's only been more recently that there's been a variety of metrics developed, but for the longest time, burn severity was something you could do from Landsat. And you would take spectral reflectance in the near infrared and spectral reflectance in the shortwave infrared or the mid infrared, and difference the two of them as if you would something like an NDVI calculation, where you're essentially swapping out the red band for the mid infrared band. And so it's a normalized ratio, and it does a great job of actually measuring the vegetation loss, so the reduction in photosynthetic biomass, because we know healthy green vegetation reflects very strongly in the near infrared, and it actually typically absorbs quite a bit in the shortwave infrared due to the water in the plants. But a burned landscape has the opposite. We don't reflect a lot of near infrared light, but we do reflect a lot of shortwave infrared light. So we use those band ratios to actually create something called the normalized burn ratio. And this has been around for over 20 years. I think it's been in use since the late 90s even, to try to measure burn impact and burn boundaries of wildfires. Traditionally done with Landsat data. Now for this project, we went and we used the Sentinel-2 multispectral imaging instrument from the Copernicus project and constellation of Earth observation satellites. And the reason we chose this over Landsat was it has a slightly higher spatial resolution, so 10 meter in the visible and 20 meter in the shortwave infrared. And it also has a decent revisit time. So the key with getting a good metric for burn severity is having imagery before the fire and after the fire. So a high revisit rate is really important to be able to measure that as closely to the before and after event as possible. And I'll talk a little bit about what can go wrong if you don't have good imagery before and after, and how it can bias or give you some false readings on your burn severity. But Sentinel-2 has an optimal revisit rate of every 5 days with both satellites in orbit. And that's a little bit more frequent at more northerly latitudes versus the equator. And it was the satellite of choice, not only for those reasons, but also because it's freely available data. And we like free data. As a data scientist and a remote sensing scientist, give me all the free data I can get. So we'll look at the bands here because, again, this is a remote sensing group. So this talk's going to be a bit heavy on remote sensing. And those of you who know your remote sensing already know this stuff, but just taking a quick look at our bands of interest, we're looking at our 10 meter band, so band 8 in the near infrared, and band 12 over in the shortwave infrared. So band 8 and band 12 are the ones used for this normalized burn ratio calculation. So what does it look like? This is a post-fire normalized burn ratio image. It's false colored, and I've kind of inverted the scale a little bit. So the darker areas are actually a higher burn ratio. And that's just to highlight the areas that were burnt to make them look like they've been burnt. And we can see there's some lakes in there that are really, really bright. Again, it's the opposite of that. This actually got a very low burn ratio. Traditionally, you would mask out water and you would mask out clouds. And when you do your burn calculations, you want to have those masked out. For what we're doing, because we have a very high resolution inventory for our area of interest, we've already got all that information. We've got land cover classification and we've got water bodies mapped out and all of that. So we didn't have to worry about doing that at this stage in the calculation. But this is a sneak preview at the study site that I'll be presenting here. Now what you get, I should pop back and just mention here. So we know that forest fire occurred, in the south area here where it's really, really dark. A lot of fire occurred over on that eastern side of this image, but you'll see really dark patches in the middle. You'll find little tiny flecks of very high burn ratio, the dark spots. And those aren't actually caused by fire. Those are deforestation activities. That's logging and timber harvesting. This is an image taken in the fall with fires occurring in the late summer. So that's a problem. If we're trying to measure burnt area and burn severity, we want to make sure we're not getting those false positives. And as I mentioned, what you want is an image before and after. So you've got a more reliable burn indicator. So what we use is called the delta normalized burn ratio, or the DNBR. And that's simply taking the pre-fire burn ratio and the post-fire burn ratio and differencing the two of them. And that image that you're seeing there is the color infrared on the left, false color infrared sentinel imagery of a wildfire, and the DNBR raster map on the right side. That black line is the boundary of one of the sub areas of the forest management area that we're going to look at here in the results coming up. I could probably give a whole talk on the limitations of forest fire burn mapping from space. There's a lot to digest in there. I won't go into too much detail. This is definitely worth mentioning though. There's other disturbances that get picked up. So if you've got imagery before the fire and after the fire, someone's built a road through there, that'll get picked up because you've removed the biomass. It won't be the highest value on your burn metric because the shortwave infrared does reflect higher for char and scorched earth materials, but it will show up potentially as a false burnt area. And so that's something to be aware of. It's recommended to have no more than a 2-month window for your before and after imagery. Once you get beyond that, you start to have other vegetation changes showing up, with vegetation phenology being a big one. So in the project I'll show here, we've got good imagery, cloud-free imagery in the summer, so end of July, and we got cloud-free imagery again at the beginning of October. And of course, here in Canada, it gets cold in September, and the plants, the deciduous and the broadleaf plants, dropped most of their leaves in that time. So they showed up with a high burn index, even though we know there was no fires there. And there's ways to correct that, and I'll mention that, but I won't go into much more detail than that. The other thing to be aware of is that thresholding and determining where the burn boundary ends can be very subjective. In addition to that, classifying breakpoints and saying I've got low burn severity, high burn severity, those breakpoints can also be very subjective. And each group tends to make their own classifications. If you scour the literature on burn severity mapping, you'll see it can be anywhere from 3 classes to 12 classes or more. So it all depends on the application at hand, how much resolution you want in that index. And there are some efforts to standardize this more and more, but it's something you have to be aware of. So for the purpose of the project we tried to follow similar classification breakpoints as the government of BC, the Ministry of Forests does. But that's something that you need to decide for your own purposes. In bold here on the bottom is an important note. There's not good research on how tree composition, stand structure, the vegetation that's there on the landscape influences the degree of severity that it burns. And part of the reason is we normally don't have very accurate, high resolution ground data outside of a few ground plots on what's there before a forest fire takes place. So this is something that we got very fortunate in a way. Obviously a wildfire of the magnitude that hit this site was not a good thing, but we were lucky that we had very detailed inventory information right before the fire occurred. It's worth mentioning here, this changes to monitoring trends in burn severity. This is a paper worth reading that talks about the improvements that have been made to burn severity mapping from satellite by the U.S. Forestry Service, and it addresses a lot of these issues. So I mentioned we don't have good ground data usually, right? We have a few small plots that might have been burned where we had good information about. But other than that, there's not a huge database on this accuracy of predicting burn severity from space. So here's a few plots. They're a little bit outdated. They're from 2005, but essentially on the ground, there's been an index developed called the Composite Burn Index. And that's a way to measure the vegetation disturbance on the ground in a standardized way, specifically to compare to satellite or remote sensing based measurements. And so there's decent correlations, and more studies are coming out now showing that burn severity predictions do line up very nicely with ground observations, but there's typically a lot less confidence in the low and moderate severity burn classes. And what that is really differences in vegetation that will respond differently to fire, spectral reflectance and spectral signatures of vegetation vary considerably, you know, from a forest to a grassland. And those low severity fires are widely variable in their spectral properties. And so we can correlate high impact, high severity burn information from satellites very, very nicely with ground data, but there's a lot more scatter when you look at the low severity. So I wanted to show an example of setting a threshold. So we've got our burn index and we want to set a cutoff to say, okay, from this value forward, this is a burnt area. There's my wildfire burn boundary. Below that threshold is not burnt. But that gets confounded when other things on the landscape change. So this image here on the left is a burn ratio raster, and we've assigned a burn status based on a single threshold to the microstands. So on the right side, we've got all the microstands that were above an average burn threshold. And there's a whole bunch of false positives showing up. So we dug into those and discovered, yeah, sure enough, those are aspen dominated stands. And based on the time of year, they had dropped their leaves and they showed up as false positives. So how do we solve that? Well, we luckily had the species information. We were able to just remove deciduous species from our burn delineation and lived with the fact that we may not have accurate burn boundaries for deciduous stands. But another approach we took in reducing that uncertainty and the false positives of a burn boundary was to take the top, I think we did, 25 percentile in that burn index. So the top severity numbers, and we assigned a point to that. So we created a vector for every pixel that was above that 75th percentile on the burn ratio. And then we threw a buffer around it, a 500-meter buffer, and said, we know for sure there was a fire in here. These are the pixels that are speaking the loudest. And then we constrained our burn analysis within those boundaries and only included microstands above a threshold within that bound. And what that let us do is, I think we removed over 90% of our false positives just by doing this. And the end goal of doing that was to automate the process and create a rapid burn boundary polygon. And once we do that, and we then include just the polygon or the microstand polygons within those burn boundaries, we were able to get greater confidence in our classification of where the wildfire extent was. Now, all of those limitations I mentioned have been addressed in the academic world of burn severity mapping. There's a whole bunch of other indices that are out there now. I encourage you, if you're working on a wildfire mapping project, to look at these different indices. Things like the relativized burn ratio, the renormalized, modified burn ratios. One that's very interesting is this burn area index specifically for Sentinel-2, the BAIS2. That figure there is kind of the workflow or the framework that was developed specifically for getting an automated and rapid wildfire burn boundary based on that, that burn area index workflow. And they throw in additional red edge bands to try to constrain some of those false positives and refine that burn detection. Okay, so we are 40 minutes in, and now we get to our results. So I may not have time to get to all of this, but I'll touch on the most important things that we did and what we found here. So the Chinook Community Forest is located close to the west coast of British Columbia, more to the north or center of the province. And this was a 130,000 hectare forest management area spread out over a few separate areas there, pictured by the red polygon boundaries. And we did an inventory there, a high resolution inventory in 2018. 2017 and 2018 were big wildfire years for British Columbia, the two biggest on record, with over 1 million hectares burning each year. And in 2018, a pretty good wildfire came through this region. Anyone's familiar with the Caribou region or Burns Lake in British Columbia. So it's a mixed temperate conifer dominated forest, a lot of Douglas fir, interior Douglas fir, a lot of spruce. And there's a few different climatic zones across this forest management area, but that's the dominant type of forest there. So we got kind of lucky that we had a natural experiment. We had done our LiDAR surveys, we'd done our aerial mapping, we collected all our ground plot data, we had all that in place, and then the wildfire came at the end of the season. So we were able to create the inventory and then measure the impact after the wildfire. So, and there was lots of questions that came up after that wildfire burnt. How many, the obvious one, how many acres burnt? Do we see patterns in land cover and the different vegetation types with how severely the wildfire burnt? Are there stand structure or composition indices that are correlated to really, really severely burnt stands? Along that same line, was there climate or terrain indicators that correlated really highly? And then taking that information, can we actually predict how severely a stand might burn in the event of a similar fire? And can we target management to those areas that are at higher risk? If we've got very high value timber areas and they're predicted to burn more severely than others, we might put a fire break in around there. We might target some thinning in that area to reduce the probability of a stand replacing fire event. So those are the management related questions to the research that we did here. And on a high level, what we did is we did this index mapping. So we were doing the observations of burn severity, taking the spectral change before and after the fire. We're then modeling based on all of the parameters we were able to use to develop the inventory and the predicted attributes in the inventory. So as I mentioned, we've got our stand structure. I should mention we develop hundreds of indices or attributes, I should say. For every one of those microstands, we've got proportions of live dead. We've got merchantable volume. We have, of course, our core metrics like our DBH and our quadratic mean diameter. We've got species distribution. We've got crown cover. You name it. If there's an attribute of interest for a stand, we've got it. I think we total about 130 attributes for every single microstand in our inventory. So we had a wealth of data to work with to relate what was there on the ground to how severely it burnt. And so that was the modeling. And then we predicted. So we went and said, can we just roll the model we've created out to the whole landscape and make management decisions going forward? If it's a high risk wildfire year, managers can go back and take this this model and target their efforts more effectively, more efficiently. So that's what we did. We went and this is some imagery from Sentinel Hub. If you're ever looking for wildfire satellite imagery, go to the Sentinel Playground. You can zoom around and take a look and preview data before you download it. It's a pretty handy tool. So this is zoomed way out. There's a few swaths of Sentinel over the Pacific coast of British Columbia, and you can just see how much smoke there is sitting in the valleys. This was August 20th, 18th to 20th, 2018. Our region of interest is this really, really smoky area in the upper left-hand side. Zooming in a little bit more, you can just see the fires burning away. So needless to say, people were not getting a lot of fresh air that August. And then looking right over the forest management area, you can see in the true color imagery here, just the scale of some of these blazes. Going to a false color, you can actually now see where the landscape has burnt. And you can see the darker areas have burnt, and in among there are patches where the vegetation looks relatively untouched. So this is really, like, looking at this imagery was really what made us think, are some of those stands fire resistant? And if so, what causes them to be more fire resistant? Is that just regrowth? Is that, well, I mean, in this case, it wouldn't be a regrowth because it's as the fire is passing through. But it was surprising to see so much vegetation within the burn site that was not really affected to the same degree. So here's the results. These are results first, and then I'll do a little bit more talk on the methods. But essentially, we surveyed 2 million hectares with satellite imagery all around that region of interest. There was over 250,000 hectares of burn scars that came through. Luckily for the foresters, only 7,300 of those hectares actually burnt within that forest management area. 80% of that burnt area was treed, and 90% of that was upland. We found 88% of the area just had mild or moderate severity burns, but 12% of it had very severe burns. And that correlated directly to 40,000 cubic meters of merchantable timber. And so there's a URL there at the bottom for those of you who want to read the whole report, because I think we might run out of time here. But that's available there on the Chinook COM4 website. It's got all the details of this project. So the burn boundary was relatively easy once we figured out how to weed out the false positives. There's an example of what that burn boundary looked like. And that's, yeah, 7,300 hectares. And it was just 3 areas that got hit by fire within the forest management area. A little bit on the southwest, a little bit more on the southeast, and then a separate area more north to the northeast. We broke it into 3 classes. Well, essentially 4. There was the unburnt areas within the burn boundary that showed very little impact on the vegetation, that unburnt class. But we had low, moderate, and high severity classes. Again, we didn't want to break it into many more classes than that because there is a lot more uncertainty in what those actual classes mean on the ground once you get into the low and the moderates. The nice thing about our inventory, as I mentioned, is that we've already done land cover classification. So for every microstand on the landscape, we've got land cover class as bare land, no vegetation, water, treed, non-treed. We saw that the vast majority of the area that burnt, as I mentioned, I think it was 88% was treed, with a smaller proportion being the non-treed. Interestingly enough, and in line with some of the research, the proportion of the area with the highest burn severity on the land, or the non-treed land base, much higher proportion of high severe burns than in the treed. And so this is speaking to a little bit about some of the limitations of the burn indices used, and why some people have started using a relativized burn ratio to actually separate burn indice severity classes based on vegetation type. So that, I thought that was very interesting and worth mentioning. We also have landscape position in our inventory. So relative position on the landscape, upland versus lowland or wetland. And on our web viewer, which I won't have time to demonstrate today, but this is a screenshot from the web viewer. We have our hydrology network as well. And we see that over 90% of the area that burned was actually in the upland class. Breaking that down a little bit more, we've got just about 5 times the area in the upland had the highest severity classification to burn. So we all know landscape hydrology, upland is typically drier, moisture limited, and that would make a lot of sense why we're seeing higher severity burn indices in the upland vegetation. So a lot of the results we found were kind of intuitive, but typically there's not been a lot of data to support the presumptions of of how the landscape breaks down based on burn severity, which is why we did this analysis. So we also break down vegetation type. You know, we do our broadleaf and our conifer for the treed. We do our shrubs and low-lying wetland vegetation. And we broke that down by burn severity as well. Vast majority of the area that burned was conifer, which makes sense. It's a conifer-dominated forest. And what was interesting was there was a very similar proportion of low, moderate, and high severity burn class observed for each of those vegetation types, the shrubs, the conifers, and the broadleaf. This was a figure I put as the kind of the abstract figure for the talk. And this was kind of a key reporting metric for this work that we did, was how much of the merchantable volume was affected with high severity. We know that the highest burn severity class typically correlates with tree mortality. And so it's very likely that these high severity burn areas had stand replacing events. So for every microstand, we break everything down into diameter classes. And we know that anything over about 12.5 centimeter diameter is a merchantable tree. And so we could actually break down the merchantable volume losses by species. And so this was kind of a big impact finding. You know, we see that there's a lot of spruce on the landscape and a lot of spruce got impacted. Similarly, we don't have as much of the other species, but we do see a similar spread between the severity classes for each of the species. So we are coming up on our hour. I'm not going to get too much into the weeds on the modeling that we did. So I'll skip right to the results. And basically, we took a whole bunch of terrain indices, stand composition and stand structure indices, climate indices. We ended up with 128 variables that we thought would be related to predicting burn severity. Through an elastic net regression, we were at a variable selection routine using some machine learning and cloud computing, because we're dealing with very large data sets. And we have a wonderful team of cloud software engineers. We were able to run a model that brought it down to 30 key predictors. And we were able to apply the prediction with good confidence. We had 70% accuracy doing a validation on the areas that did burn, to 92,000 hectares of remaining treed areas that were not burnt, to say, in the event of fire, how likely is it to be a stand replacing type of fire that takes out this forest. What we found was that there was almost 15,000 hectares in the highest burn risk severity class. So we rated every single microstand with a probability of this very severe, almost stand replacing event, and able to identify that spatially for the forest management team. I won't get into spatial autocorrelation, but you know, safe to say we accounted for that. That's key to our inventory modeling approach as well, so to make sure we're not dealing with spatial autocorrelation. We know that everything in geography is related to everything else. Closer things are, the more related they are. So spatial autocorrelation was accounted for by doing a sub-selection of the microstands in the burnt area. Here's a list of the number of variables we actually used in the prediction model. A lot of them were structural variables of the stands themselves. Many terrain indices. We use an approach using the LiDAR-based digital elevation model at many scales. I think we go from 1 meter all the way to 2 kilometers in our kernel analysis of the landscape. And these indices we use are very strongly related to hydrology and site productivity. We also have climate data and the composition of the stands as well in terms of species. This stuff is in the report. So anyone who wants to come back and look at what we found in terms of trends in burn severity with the terrain can go take a look at that and report. I'll just say here that we found that higher sloping terrain had higher burn severities. It's likely related to the fact that more upland area burnt. But we know that slope can influence fire propagation, and that's likely what drove that relationship. Our prediction analysis, because I'm running out of time, we'll just say it's complicated. It's I'm happy to talk about the data science behind all this another time, but we used a very sophisticated variable selection routine and an elastic net framework. So what did we find? Here's your takeaway. The strongest predictor of burn severity was the average autumn temperatures and the number of frost-free days, or when the frost-free period ends in the year, I should say. So turns out that the higher elevation stands, they burnt more. And that's an upland relationship. That's a moisture availability relationship. But for stands that get colder earlier in the year, their risk of burning was highly reduced. And so here's a list of the key predictors. Dead percent was a big factor, the percent dead in the stand. You can see 1, 2, 3, 4 down that list. 20% dead for the lowest burn severity class, up to 42.5% for the highest severity burn severity class. So we know snags and standing dead and lying dead do relate to fire impact and fire propagation. And we have more work to do to tease that out. But this is what the results look like when we predicted across the whole landscape. And this is I believe this is my second last slide. And so we found areas that had a lot of high risk stands. But interestingly, there was lots of areas of very low risk as well. And so, I mean, the next steps here are essentially when the next fire hits, we can do more validation work and see how close our predictions were to reality. There's a lot of assumptions in the modeling. You know, it has to be a similar type of fire condition. It has to be a similar, you know, weather year, fire weather year. There's a lot of limitations in doing this type of prediction. It's very forest specific, so the type of forest we're dealing with. And this is not a model you could just apply to anywhere, right? It's a very site-specific model that would be used for these forest managers and for forests of similar structure and composition. There's the web URL to our viewer, which has you know, an interactive map where you can go in and get all these attributes for every single one of our species of our microstands. Breaks everything down by species and age, site productivity, structural variables, land cover, as I mentioned, the list goes on. And we've also got our fire severity predictions on there as well. And I'm a bit long-winded, but we're gonna call her there. I don't know if we have time for questions, but I'm available to stay on the call if Tony is up for it.
Sure, that's great. Thanks very much, Cassidy. Any questions? And maybe Cassidy, maybe start with, looks like a question in the chat from Jesse. Maybe you could speak to that.
Yeah, let me pull that open. I will read the question out from Jesse. I think it makes sense for non-treat areas to see very high burn severities. In this area, it's possible some of these have been cleared recently, had a lot of slash. That's true, it's a good point. The other factors could be lower stature plants. Yeah, so those lower stature plants can have higher burn severity, greater vegetation biomass loss. Yeah, that's exactly why there's been the development of some other indices like the relativized burn ratio, where you take ground measurements of this composite burn index for each different type of vegetation class, and you correlate those to the burn indices, and you don't have this spread across the different land cover types. You're essentially calibrating everything to that vegetation class to account for that. And we didn't have data like that in this study or in this project, but it's something that I think is important for trying to make sure that you can quantify those severity classes to the on the ground metrics. That's the name of the game, is validation when we do remote sensing.
Indeed. Any other questions? Cassidy, I have a question related to the modeling approach. So your predictive, probability-based modeling approach. How would you compare it with, more of a standard or traditional approach using random forest, where you've got a whole list of covariates, various predictors, and you kind of throw the kitchen sink into the model, which it sounds like you're doing here. But could you briefly compare and contrast, what are the benefits to your approach over a more traditional random forest modeling approach?
That's a good question. So I myself wasn't running the modeling. I know enough about our HRIS predictive analytics engine to be dangerous. But if I misspeak, I'll have my colleagues clarify. So this is a workflow that's been developed over many years of research on taking hypervariate analytics for prediction for inventory modeling purposes. And there's a lot of reasons why we didn't use a pure machine learning random forest approach. There is more and more people using random forest algorithms for forest inventory predictions. Some of the limitations lie in the difficulty in tracing back your steps and having I guess removing the uncertainty of the black box of the regression trees is one of the concerns. In British Columbia, the regulators for forest inventory are very strict on what types of analytics are used for reporting and regulatory purposes. And so machine learning algorithms are starting to become more acceptable from regulatory perspective, but there's very much a shyness of black box solutions. Even if they can predict better, they're less traceable and less, I guess, quantifiable in some sense. So we've done random forest modeling and we can get good predictive analytics from it. There seems to be limitations on reproducibility. And so this is one of the reasons why we've taken this elastic net penalized ridge regression, I should say lasso and ridge regression techniques together to find this kind of sweet spot in the model complexity, between the model complexity and the total error and bias. And so, I mean, Dr. Ian Moss has pioneered this approach. We've at Tessera, we've taken the methodology and we've turned it into a more automated, cloud-hosted, scalable routine, data analytics routine, so that we can do these type of predictive analytics across millions of acres of data points. But we're continuously improving it, and we have played around with other machine learning algorithms, but the short answer is you don't want to move too quickly against a regulatory approval. Otherwise, it doesn't always. People don't always pick up on what you're putting down.
Right. Yeah, that makes sense. Thank you.
Yeah.
Any other questions for Cassidy? Have a few thank yous in the chat as people stepped away. Thanks everyone for joining us, and again, thank you, Cassidy. That was great. We really appreciate it this afternoon. So that'll be it. Thanks everyone.
Great. Thank you all for your time.
Thanks again, Cassidy.